Hello guys and welcome to Simulogical. Today we will be performing a simulation on the vibration of a tuning fork. A tuning fork is a precision instrument that is used for various applications. The major of this application is the use in musical instruments in order to determine the frequency generated is within the right range. First I shall begin by the sketch. The two circles which are drawn will form the central body of the fork. Give the desired radius for the inner radius and the outer radius. The distance between the inner and outer circle will determine the thickness of the prongs of the tuning fork. The straight line will determine the base of the fork. Tuning fork was previously built by expert craftsmen and today it is made using accurate and precision machine. A tuning fork's use in the musical industry is indispensable. The vertical straight lines will form the prongs of that fork. Now we will extrude this sketch. Let us move on to the setup. First, we will generate a mesh. Right here in the setup, we can choose the element size that is required. I will choose 5 mm as the first mesh. It is quite a coarse mesh, so I will further refine the mesh. Refinement of the mesh will cause an increase in the number of elements and nodes, which in turn causes the accuracy of the solution. But more the number of elements, the longer time it will take for the computation to solve. Yes, the number of at 1 mm mesh size, the number of elements have increased quite a lot. Let us now give the structural supports. I will give a constraint of fixed support to the base of the fork. In the setting, we can select how many modes of vibration we need to find. By default, it is at 6, but for right now, I'm going to turn it to 3. In solution, we will have total deformation. And click solve. The solution is done, and now we can see that the deformation is from side to side. The time lapse shows that the deformation of the prongs is from side to side. We can see that as we selected 3 modes, there are 3 frequencies that are solved. Now select those 3 frequencies, right click on them, and you will find an option called Create Mode Shape Results. This will create the deformation for each mode. We'll have to hit solve again. This will only take a few seconds as the solution is already converged. Now you can see how each mode of vibration takes place. The primary mode of vibration shows which is the most significant of all. The second mode of vibration is that the prongs move from inside and outside. For the third mode, the prongs move front and back. Now one can keep in mind that we selected 3 modes of vibration, and hence only 3 modes of vibration are displayed. But these are not the only modes which exist. So now I will select 6 modes of vibration, and for that I will have to first delete this deformation and put in a new one. As the number of modes of vibration has increased, the solution will take quite a bit long. So as we can see within the tabular data that 6 modes with 6 different frequencies is presented. The primary mode remains the most significant and is shown in the total deformation. Again, we can create the shape mode by right click. The first 3 are just the similar ones. The first one moving inside and outside. Sorry, the first one being sideways, the second one inside and outside, the third one back and front of the mean position. The fourth one is that alternatingly prongs move front and back. The fifth and sixth modes are quite peculiar. The fifth one is the sideways bending of the prongs, and the sixth one is the rotational along the longitudinal axis of the prongs. It should be noted that the final deformation that is seen is the combination of the number of modes of vibrations, and the primary mode of vibration is what we hear. A tuning fork also produces sound within the supersonic range, but is not within the audible range.